Share the screen. All right, so we're back. So this is part two of our baby RLHF PPO, right? So we've already discussed several parts, and I just have a few more things that are happening in the functions, and then we're going to put everything together kind of to generate. Keep in mind, it's a simulation of a GPT, so some things might look a little quirky in how to generate the language, but the idea is still there, okay? All right, so we were in the collab, and I believe, guys over there, any questions? Guys in the back over there, question? So what was the last thing we did? I think we did the probs of next token, the log prob, and we were adding things to the list. So old log probs here, I think. So we were, I believe here, right? So we yeah, here. Okay, so let's just start here again. The reward function, remember, is just a heuristic rule. If I get an ID that is 2, it provides a 1. You can see that there. So if I use temp, this provides a 1. That's my reward. I just have a simple heuristic rule. But if it's just 8, I think, is the token, so then it provides a 0. And this is the information that I'm going to need for PPO. So PPO will need the old log probs and the new log probs for the ratio, and then the reward. Okay? And then there would be the essence of the distribution of the current model versus the initial model, which here I'm still just using old log probs, new log probs, but it would be the same. Keep in mind, this works really perfectly because you're always just comparing either the input and output of the GPT or just the output of the GPT. And if you remember, that's a fixed tensor, right? The first thing you learn when you learn the GPT is that it was, think always of a tensor n by 40 by 512 moving through. So n by 40 by 512 went in, n by 40 by 512 came out. Always, right? Until we have the final. So you could do it at that stage, possibly. Those are the embeddings. But here we're using it on the final distribution, but that still would be n by 40, not by 512, but n by 40 by 50,000. Do you guys see that? So they're always consistent. Make sense? So you're always then able, this is like one thing that just works nicely about it, right? Because the model is always fixed in that sense. And all right, so now, and it can be across batches and so on, and that also works nicely. All right, so we did this. We can look at the token, which I believe is currently 8. Whoops. That's 8. Let's add a few more cells. Okay. So that's just the same. I was just going to show you that this actually does. It's like an if statement. So if it's 1, and oh yeah, token IDs. That's not the fun. Okay. Sure. Maybe it needs to be a torch tensor. There, yeah. So, and if I change this to 3, yeah. So it's just a heuristic rule that I'm using for my reward function in this case. You know, when people do work in reinforcement learning before this idea, they would spend a massive amount of time trying to figure out the reward functions. Do you see what I'm saying? Let's say that you're trying to train a self-driving car. Think of everything, right, that you have to think about to provide that reward. And so it used to be a lot of work, but the nice thing now is, you can train neural networks to kind of do it, etc. All right. So yeah, so historically, like if you went back, you would see how difficult it was. All right, another thing that will happen in the code is that we're going to have a list of rewards. So actually, you may not know this about reinforcement learning, but in reinforcement learning, if you ever did research in that, you would come to a point where you're like, how do I even evaluate the performance of this? Do you see what I'm saying? I showed you in one example for the homework that we were using that BERT scorer to actually get the scores, right? And that's one way. But in reinforcement learning, as it turns out, you can use the rewards to measure performance. So essentially, rewards, you want them to be good, right? 1. Because 1 means you're predicting that it's a cat, and you wanted it to be a cat. You said, I want you to predict ID 1, and that's when you give me that's when you get a high reward. So essentially, you plot the rewards, and that's kind of what I'm doing here. I'm taking a list of the rewards. You see 0, 0, 0, 0, 0, 1, 1, 1, 1. So the performance went up. Do you see that? But if it's 1, 1, 1, and then 0, 0, it's actually going down somehow. And so traditionally, that has been the metric used for reinforcement learning. Okay, so we're going to keep track of the rewards, but also we have it available for our process. Okay, this just the generated IDs. You might see that in the code also. And generated just means the values here. So this is another list, and you can see here I've been accumulating the number of generated IDs. I could have done that for the reward, I guess I did. You can see there's actually 2 in there right at this time. Notice also, this is a good point. Actually, this actually helps me out a little. Why is 1 0 and the other ones are 8? Because 0 was the beginning of sentence token, right? So remember that in the GPT and during the generation, you drop like this one, right? You pop off 1, right? As you're generating and advancing, so you could do that, right? If you want to keep that fixed, like the size, you put in a new one here, drop the old one, and so on. But that's kind of like the sequence that has been generated. All right, we're going to have this idea of prompt. Currently it has 1 value in it, but I can concatenate values to the prompt as I'm generating language. So keep that in mind. Next token, for instance, that should be an 8. Right, so I have a 0, and then the next one was an 8. So if I want to now append that to the prompt or something, you can use torch cat concatenation. So prompt next token. And now they have been concatenated. Do you guys see that? So this is kind of simulating that whole idea of language generation. Okay, so you're providing question answer, or the cat is sleeping on that table. All right. So I broke it out like this so that we understand what every line of code is doing when everything is put together, and it's just easier to understand. So I printed these. I printed both of these. Remember this trick. If I want to pop off the first one, like the beginning of set, I take generated, right, and I just slice excluding that first one, for instance. And so now I don't have the 0, right? So These are just trying to simulate the behavior of the GPT. All right, so that's done. So rewards here, we may need to stack it. So let's actually do. Let's take a look at rewards and what it is. Okay, so we have two things like that. Two tensors. Remember that with this, the dimensions are always a problem. So some of these things were just so that it runs. Okay. But there you are. I stacked it. And then I'm going to do. Oh, it's probably because the stacking. Yeah, that's what it is. Sorry. Let me. I ruined it. Did I ruin it? It's. You get the idea. I think I ruined it. Yeah, because now it won't. I've modified the structure of it. All right. But anyway, once we run the code, it should be fine. Okay, so here's the old log probs, right? So let's think of it just to remind ourselves. We have some probabilities, right? This would be like the probabilities, the softmax. It's a torch tensor called probs. And then we run it through log, right? So torch.log probs, we've already addressed why we can do this, and this is what we can call the log probability. So you can see how that's the terminology that, and probably if you read the paper, as I said, they'll refer to the log probs, and that might confuse you, but there we are. You see that? So it's changed. Now it's like 2.3, 1.6, bigger numbers, but also you can subtract instead of taking a ratio. So that's the mechanism. I think I printed it already. Then the torch stacking, this is just because, like I said, so that the dimensions worked out. Should be values in there. Okay. Not sure why this is giving me an error. Let me try log prompts 2. All right, so I think the code did run that, so not sure what I messed up. But anyway, so that's the last of it, okay? The last of the operation. So now this would be the actual function that we would use. So let's take a look at it. Just going to grab, well, I'm going to grab the whole thing, actually. I think I had a dimension error, but hope I don't. All right, so this is actually the last part. So everything that I did before, I was just like looking at every single line of code, making sure things would run. Here I'm just using them again, okay? So remember the key parts, and let's just rerun these parts to make sure they're still functional. So I had the libraries, the tiny policy, which represents the GPT itself, which we have discussed, the fake reward function, and the PPO loss function here. Okay, and then we initialize some parameters. After that, I just started breaking into all the individual lines of code. So we would skip that essentially, and then we can come to the actual for loop. Okay, so this is the actual for loop. Notice that I'll go do a high level of it first, and then just kind of discuss some of the parts. So first of all, you have to set a number of steps. All right, so this is just the process of think of it as letting the model do its thing, right? So, let the model, perhaps it has questions and answers, and that's what you provide. In this case, this example just starts at something, starts generating, okay? So remember, it's not gonna be, here's a simulation, essentially, okay? But, so we're gonna do this 300 iterations. I have the prompt, which was 0 as we discussed, some kind of generated thing, and then we keep track of what is the old log probs and the rewards. This section here is just to generate, like a GPT would generate some text, okay? So we can look at that. Then we accumulate values in old log probs, okay? We can run with a reward for each prediction, keep track of that. Then this section here simulates the generation of the new log probs, as we need to have also that, right, in some fashion. And then once we have all of that text together, then we just provide the new log probs and the old log probs and the rewards to the PPO loss function, and the PPO loss function then calculates a loss. And this becomes similar to how we have trained other models with MSE or cross entropy. Do you guys see that? From there, we have an optimizer that we already instantiated at the top, loss backward, right? Calculate the derivatives, and then optimizer step, which does the update of the weights. Does that make sense, guys? So that's essentially what's happening. And then here, we can print the average reward, etc. Remember that this is how you would keep track, right? So in the simplest case, let's say that we want to always generate that what we want is for the ID to be generated is we want that ID to be 2, and that means cat. So in the extreme case, if it never generates a cat, the rewards are always 0. So we know it's pretty bad, right? If half the time it generates cat, then the rewards are like 50-50, right? And if eventually it just starts generating cat all the time, then now the reward is just a 1. Do you guys see that? So that's essentially, and you can keep like an accumulated reward or whatever, but you know from there that the model is working. Got it? Do you guys see that? All right, that's it. So you can see that it's got 3 parts. It's got the PPO loss part, which, as I've discussed, is the new logs versus the old logs, and the reward. It's got the learning part, and this is just essentially printing whatever the rewards are, the mean of it, and then you can see print the loss actually, and print the average reward, which should be. Am I missing? I think I didn't copy that last part. Huh? I meant, oh, yeah, it's missing, right? So, yeah, sorry. I guess I didn't copy the whole thing. This is just a print statement of printing the reward given the loss function. And that's how you evaluate, as I said, reinforcement learning, by looking at the rewards. All right, so now let's take a look at, I'm almost scared to run this now because it was giving me that error. No, it worked, right? So it worked. Why is there input in here? Let's see. I think I had an input somewhere. Yeah, I have an input in the loss. That's why it halted. All right, so let's try it. So I swear that I tested. Okay, I didn't run. I have to rerun the cell. Okay. Now let's try it. Okay, so I got a green check. Yeah, okay, good. So it does run, which is good. Look, it's got all ones. Job's done. Can all go home, right? So that means and this is what I was saying. How do you know in reinforcement learning? How do you know if your system learns? It seems like a trivial question, and you almost like, no, I'm sure there's some kind of F measure I can calculate, and then you really get into it, and there isn't, right? And so how do you do it? And so the reward provides that feedback. And actually, in the BERT model, in the TRL example, I was using the BERT scorer, right? You guys remember to provide the score, but that's also a reward. So we were measuring performance based on the reward. All right, so you guys saw that it happened. So now let's take a look. So we know it works, which is good. So no errors anymore. I don't know why it was giving me those errors before, but as you can see, and it's here we are. So let's kind of walk through it. So we could, essentially we are first of all iterating through. These are just like, I think this is usually called episode. It's just playing games, right? So for instance, in reinforcement learning, you would, let's say you're playing a game, right? You're training this in a game. So chess. Someone brought up chess. So what do you need to do first? Start the game of chess. So you start, you're going to play let's say you were going to play 100 games of chess, but you have to start at the beginning, right? So you do one whole game, come to an end, or win or whatever, then another game. So you do, all right, I'm giving you 100 moves to play, but there's also 100 games, or 200, let's say 200 games, and for each game you get 100 moves. Do you guys see that? So that would be 2 for loops. That's how you control it. So in this case, we're just saying we're going to do this like 300 times, okay? So what's the sequence? I have to start with some prompt. I have to have the generated. And then here in this example, this is just trying to simulate GPT logic. It's generating 8 tokens step by step in sequence. Do you guys see that? So that's the idea. So how does it work? We have a prompt, right? And correct me if you guys see any issues. But we have our prompt, the beginning of sentence token. We give it to policy. What is policy? That's our GPT. And it gives us our logits, right? Okay. What do we do with those logits? If you remember, we run them through the softmax. You should know that creates the probability distribution, adds up to 1. We would normally use an argmax to pick the ID of the highest probability. But if you notice here, I give probs to this multinomial function. We already described what it does. It should, most of the time in theory, select the highest probability, but sometimes think of it as picking something random. And why is that important? Because you want to force it not to always make a left, right, and make a right sometimes. That's called in reinforcement learning exploration. Very important component. Also, we sometimes have to do tricks with these special functions because we cannot break differentiation, right? Remember that this needs to back propagate to do the optimization in the neural net if we break back propagation. It's not going to work, right? So that's why we have to do it. So I have my next token over here that has been predicted. That's the ID. But notice I'm kind of going back to the thing I had, right? Because I don't need the ID here. What do I need? I need, in this case, for this example, I need the probability of it. Do you guys see that? So in this very simplified version, I'm just taking the probability of the ID that was selected. Got it? It's not, like the best approach, but just to give you some insight. It would probably be better to have the whole tensor in there, right? So yeah, so here you can see, but in this example, next token, just to keep it simple, goes back to probs and gets the probability, okay? And then now, what do? We don't use the actual probabilities, but we run it through log to get the log prob. Does that make sense? All right. Then I have a list of all log probs because I'm doing one generation, you could argue, given a question. So I just append it there. Okay? Again, I know you're probably thinking, but it's a simplified version of it. Now I have so this is keeping track of the old log probs. Then over here, notice that we also need to have a reward associated with the token that was generated. That is at the ID level, if you remember. So I just give whatever this was, 7, let's say, goes into fake reward. And this is just a list, so it gives us a 0. That's the reward is 0. Okay. And then as far as the generated, we actually keep track of the ID itself, right? Do you guys see that? Make sense? And then we should do this in a loop for 4, okay? And then we're also, to the original prompt, which is this one over here, which it started at 0, we are now providing the new generated one and whatever was in the prompt, right? And we're just concatenating it to it. Make sense? All right, so we can now, we have generated, we have rewards, and we have old log props. So we have like our 3 variables here. Okay, we just populated those 3 variables. So now we make a few modifications, the squeezing and all that for the shapes. So notice over here, we take generated. That's this one over here. It's got the IDs. Notice we do some slicing. We just get rid of beginning of sentence, beginning of sentence token. And we call it generated tensor. We run it through torch tensor because, as you know, once we get into that whole computational graph, it does need to be all in torch. The rewards also become stacked, okay? And some shape manipulation. We got our rewards. And we've got also torch stack here for the old log props, where the old log props are the thing that goes into the ratio. Got it, guys? All right. So if I run this loop again, it'll clear everything up, so I think nothing will get damaged. So let's print out the shapes of these things. All right, so let's take a look here. So I'm going to put a halt, an input here, just to see. So, right, you guys see? So if I do print generated tensor dot shape, right? I just want to know what those dimensions look like. Print rewards dot shape. Print old log probs. Oh, dot shape. Right? That's correct. All right. So, and let's add an input here so that we let it do that whole process and just see what we get. So, sure. So 8. 8 probabilities, 8, it would be 8 generated tensors, generated, yeah, the IDs. So 8 IDs, right, for the first one, 8 rewards, and 8 probabilities, log probabilities. Got it? Any questions there? So you can see what's important here is we know they have a dimension of 8, right? And we can provide this information for the ratio. So remember, this is the old log probs idea. Okay, let's kill it. Now, we don't need this anymore. All right, now I'm going to do the second one. Usually, in a game, right, so you have a state, you have to think in reinforcement learning, right? So the traditional case is chess. You have the state of the board, so you're in the state. You give that state as a vector to the neural network, the model, and it predicts an action to take, right? That action needs to be given to the game. It's the game environment. The game environment, because the game environment has like the rules, right? So it takes that action, and what does it give you? The new state, right? So if I'm in, in chess, right? I'd make a move. Okay, you put there. Now comes the counterattack, right? So the opposing the pieces then come in, they kill you. So now you're in a new state, or you lose that piece. They don't necessarily kill you. You lose a piece, but you're still in the game playing. So that's the idea, right? So now your pawn is gone or your knight is gone. All right, so that's kind of how it works. So there's an old state and a new state, and the actions are in the environment. So here we took essentially, we did something. We got a prompt and we generated. All right, now, and we did this, so that has happened. Now in this simulation of how a GPT would work, right, we have another step that's going to take place. This is going to be the computation, compute new log probs under current policy, right? So here we're going to have, instead of old log probs, we have new log probs. We have a prompt, okay, which is the same as before. So we do for token in generated tensor. So that in this example is going to become in generated tensor we had 8 IDs, correct? Next token, it's actually telling me what's in there. Yeah, so that's what I have in there, right? So a sequence of IDs. So now instead of generating just 8, I'm just grabbing from there. It's just an example to indicate that there's been some change in the state of things. So for token in generated. So actually, let's print. So I'm going to do print generated tensor, just the values. Put an input here. Okay, so let's try that. And you can see, so it's just going to grab each of these as an input to kind of be a little bit different. So this is not meant to be perfect. Okay. So I'm going to grab each of those IDs individually. That becomes the prompt. I give it to the policy. Given that the model gives me the logits, right? Then with the vector of 10 that we had already looked at, then I calculate the softmax of that, the probability distribution, adds up to 1. Then we kind of reverse engineer, given that yeah, given that I know the token in this example, right, I just grabbed it. So I grab the probability of it, okay, from probs, and I run it through log probs to create the log prob. Do you guys see that? So it's not perfect here, but it's just meant to be a little bit different. I honestly don't know how to best do this. All right, so I have the log prob here. And what is important to understand is that this is after the other one, right? So one is old, one is new. Then I take this log prob, and again, what is it now? It's not old log probs, it is new log probs. Do you see that? There's some example here. Perhaps I would, to be better at this, I would have to I would have needed something, right? Initial, then I would do a generation, save that as old, and in the next iteration, I would do a new one and keep track of those, right? But if you guys can improve this code, by all means. All right. But yeah, do you guys see what I'm saying, right? There's got to be a change in the state. I can see how you guys are thinking. Maybe we needed to, in between these two things, we needed to update the weights so that it reflects that it's a slightly different, and that can be done, but it just needed in every, like the old iteration might have been what I stored. I'm trying to remember how maybe if I have time, I'll show you how it's done in Q-Learning, and we can improve that a little bit. All right, but yeah, this part I acknowledge is not 100% perfect. Okay, so, but essentially this is the second generation consistent with the first one. Get the prompt, get the logits, run the softmax. Now I have probabilities, run those probabilities through a log, and now I have a log prob. And then I just collect these values as being new log probs. I can concatenate these values in the prompt as before, and then I just stack new log probs here to create this idea. Okay? Yeah. And then I'm not going to need the generated tensor because I have it. And the reward, not calculating it here, but I do have this reward from the old approach. Think here of one thing. Let me think. Trying to think if the rewards should be calculated. Does that even matter if we calculate the rewards based on the new generated or the old generated? Do you see what I'm saying? Like here, the rewards are only calculated here, right? And I need to pass those. Here, I only have the new log probs. So that's something I got to look at in more detail. But let's see. So here I have, so now what I do have is I have old log probs. I have the rewards that I calculated in the last generation. And then I just have now the new log probs. Okay? So let's print this one too. So let me do print new log probs dot shape. This should be input. 8. Do you see that? So it does have the shape, right? So I have, I'm a bit, I'm wondering about something here, but you can see I've generated the old log probability, so the model, the new ones, and I have a set of rewards. So once this is complete, then you just provide these to the PPO law. So notice this takes the new log probabilities, this takes the old log probabilities, and this takes the rewards that I've calculated. They go into PPO loss. Right? So this, again, is a super simplified version of this, but you can see here, we've already established, because they're log probs, we take the difference between them, but this is equivalent to the ratio, right? So if we want, we can think of, and I believe the old is the denominator, and the new is the numerator. So that is definitely in the equation. Yeah, I never thought of this. Like, which reward do we give it? The old or the new, right? So that's kind of where I'm getting a bit confused here. But yeah, so you calculate the ratio, and then the ratio is multiplied times the reward to create the surrogate. And then remember, there's this idea of the KL divergence, but this would be at, the original. Even let's say you've done 200 iterations of updates to the policy, this here should be like at time zero. Okay, the policy at time zero. So it doesn't deviate too much from the first pre-train and fine-tune model. Does that make sense? I could have created, I guess, another variable. So this could have been like ref. So what I think actually we can modify this, because these are just size 8, right? They're size 8. So I could have policy ref, I think, and then policy ref would go here, right? Policy ref. And so the key thing is, this is a lot like how we did with TR. We would need some time somewhere here where, like the first old log probs or whatever, right? So we just make this like one time. If, what is it? If step equals 0, then policy ref, and we just assign old log probs. That would be a little bit more correct. Do you guys see that? We probably need to do it actually here, because it's going to be better formatted. So if step equals 0, the very first time, yeah, old log probs clone is actually pretty good. Do you guys understand what I just did? I just did that. So that's an improvement I could have made to the code. So I just, at the very beginning, right, I grabbed the state of it, and that's what I'm going to use as my ref. So now in here, I think I added this at the here, right? So policy ref, and this is consistent with how you guys would have had it in the TLR example. Does this make sense, guys, what I'm talking about here? Huh? Well, let's see if it works, right? So let's see if I miss something. Well, what I was saying, what I was trying to fix is in my code, when I calculate PPO here, in the ratio, you are supposed to use the current policy and just like a little bit before, right? You're just seeing this change in the updates. But when you do the KL, it's not actually old log props, like just the 2 steps ago. It should be the original state at the very beginning of the training. Actually, before the training is what I should have done. But like as you can see, it's hard because I have to get all the shapes correct and everything. So what I was trying to do is adding this parameter policy ref, which would be the original one before any of the 300 iterations happen, and I take the KL divergence, right? So it doesn't, so that the new model that I'm getting every time is not getting too far away from the original one. Do you see what I'm saying there? Yeah. And so that's key, because if you didn't have this KL divergence, by doing this ratio with these rewards, the model could change completely. Like it's going to diverge way too much to where it becomes really bad, technically, right? So it could become. So this is like a break that keeps it, yeah, you're changing it, but slightly. It's still like if, let's say that you build a model that speaks English, you want to turn it to Shakespeare. But if you don't have the KL divergence, it just like becomes incomprehensible in the Shakespearean way. So by providing this break, you are shifting it to English, to Shakespeare, but it still can retain grammar and all those things. Do you guys see that? So that's something that I should have done a little bit better here by using this policy ref. And I was trying to solve that by just taking at the very beginning a copy, because it's old log props, right? So it should have worked. I don't get. So here, right? So this old log props that's here is what I'm going to provide here. So now I'm just creating policy ref, and it is just grabbing at step 0 old log props, which is the one that's already correct. Do you see that? I'm essentially copying. So I don't know why this didn't work. Did I not run? Maybe I didn't run this, and that's goes after rewards too. Okay, so I have it in the wrong place for sure. This should be correct. Maybe that color part. I don't know. I'll have to fix it later, but that's the idea. If you guys understand, is that it shouldn't. It should really be the reference one here. So I'll revert back to old log props, and this actually should be the KL divergence, which is and that not exactly like this. I'll take this out. Okay, so that's correct now. Props, and I'm going to take this out. So it is right. Yeah, something there. I'll see if I can update it. But yeah, that's it. I mean, that, you do this, new log props, old log props, the rewards. And so just to kind of summarize here, remember, so the ratio between these two, okay, ratio times the rewards, and then that's called surrogate. So then we can take some kind of an average, etc., and then plus the KL, which is a thing from information theory called the KL divergence, and it just makes sure that like it's not changing too much from the original distribution. But again, I should have used here at the very beginning policy ref, and that's one thing that I should improve, and then so we're there, right? So it keeps doing that as a loss, that calculation. Okay, then it returns that as PPO loss. Remember, it's in the computational graph, so it's now going to optimizer, zero out the grads, loss backward, optimizer step, updates the weights of the GPT. And that's it. Does this make sense, guys? One thing that I'll admit, as I was looking at this, one thing that confused me is the reward. Like, does it even matter that whether it's from the old or the new? Because remember, it's every iteration, right? So there's an assumption there that is being, but I guess I didn't think about that clearly. So I'll have to. So do you guys have any thoughts on that? No? Do you understand the problem I'm having? So if you notice over here, I calculate. This was nice. Like this works perfect. I get the rewards, everything. But then I did this other generation, this whole other generation, and I didn't calculate rewards. So really, should I calculate the rewards here or here? And if I did, which ones do I use? The old or the new? Do you see that? So that's something that I thought I'll have to think about. And I'll let you, oh, go ahead. That's what I was thinking, because every iteration you do have these, so I'm not sure. Yeah. Here, and as I said, maybe there would only be, that's the other thing. I think I'll answer the question like this. If this was more correct, maybe, this would only happen once. Here there's two. There would only be one. Do you see that? And so what you would do is, from the previous iteration, you would save that data, right, old probs, as old probs. And then here, whatever probs is would be new probs. And its rewards. So probably then, by that logic, it would be the current rewards. It's just this is not, could have been a little bit better. But do you guys see that? And then that way, because that makes more sense, I'm thinking like in a game, that's how it would be. That's why I was thinking of the state action. So in a normal reinforcement learning, you have a state where you start. You run it through the neural network, and it gives you an action, the prediction. You give those actions to the environment. The environment gives you a new state, which means where you are now in the board. That's all that happens. So old state, new state, right? And then that new state, guess what? Is saved now as a variable called old state. You go to the next iteration, and you start there. You predict the action, goes into the game. It gives the new state. New state becomes old state. Next iteration, that's plugged in. Action, environment, new state. So this is how this should be, most likely. Okay, and the reward is happening only once, because the game gives you back your new state, your reward, and also your whether you win, you lose, and so on. So I'll probably improve this a little bit, but it covers the idea. I think that's how I should have done it. So yeah, I might update this, and as time permits, we will come back to this. But hopefully this captured the idea of PPO, though. Are there any questions? Yeah, go ahead. Mm-hmm. Okay, so the way that you're asking, you have to frame it in this context. So the way that you would know that is by the reward, right? Right? So state goes into the net to predict the action, and the action goes into the game to tell you the next state. So what you're saying is, what if I don't know that this state is better than this state, something like that? So that's the thing. The game is always telling you because the game knows the rules. So I guess that's like putting a pawn here, and what did that do at the beginning? You know what I mean? So again, creating a game. Well, you have a game, but creating the environment that governs this is hard. Okay, so and when you're dealing with something like chess, at least you build the rewards based on the rules of chess. But that's usually like a whole bunch of if statements that have to come in there that say, okay, if you did this, this is the reward. If you did that, this is the reward. So you're handcrafting those rewards based on the game. So as you can see, it's hard. This is hard, right? Reinforcement learning, when you have, and actually games were the place where you could actually build those rewards. Now go back to the example. How do you now build rewards to tell a robot to dance better salsa? Do you see that? That's the challenge. And so that's why we have other approaches. But I think your question was getting at what is the heuristic rule that tells me that this state has a reward of 0.20 equal to a reward of 0.20 over here. Do you see that? I believe that's kind of how you're asking. Anything else, guys? All right, so that was PPO. I've introduced it. We went through the whole thing. You've seen the process. So I might, have a few notes in the next class. We do have 20 minutes, so let me give you a little bit of the math formulation just to kind of try to tie it back. So I'm going to switch over to the whiteboard. Okay. So, and this is in that Siegler paper 2020. I highly encourage you guys to read that paper, and now at least you've seen the code, so you might have a sense. Okay, so so remember, here we're talking about PPO, where we have a policy because it's not always a GPT, right? It could be an agent. This is where the name agent comes from, right? So it's a neural network that's an agent, and the agent is playing in the game. In this case, we have the agent, or the policy is our GPT, right? That's the thing that we are trying to do, but essentially the term that you will see in the paper for this is pi. Okay, so whenever you see pi, keep in mind they mean the policy, and in the context of that paper, they mean actually the GPT. Okay. Remember that there's many variants, but this is proximal policy optimization. So the formulation of this one that you might see in the paper is as follows. So J, as you know, is the loss function, which it is, right? And it's going to be, I believe it's a minimization of the ratio, possibly. So, because it says min. And then you have the ratio, we'll just write it as ratio which has is based on the network, right? So you'll see like a theta there that just implies that is parameters that you learn and can be updated, times something called the advantage function. It's written like that, okay? But this is in my code, right? I had the ratio times the reward. Okay? So that's essentially, and this will be the formulation. And this actually, you'll see something else. It'll say, so it's going to be a function like this with two things. It's going to say this, comma, and then there's going to be this idea of a clip. Okay? And that clip just says that you're going to select, oh, you select the minimum of these two. That's what this is. All right, so select the minimum of these two. So you have ratio theta 1 minus some epsilon or 1 plus some epsilon times the advantage function. Do you guys see that? So what does this mean? It means what I said in the beginning. Right? Let's say that a ratio is what? 1 is the value, right, at the center, right? But a ratio could be from 0.80 to 1.2. Do you guys agree? And so we clip it essentially at these two extremes, right? So E in this, in this case, E this E is straight. Epsilon type of thing. So this E is like a 0.20, right? Do you guys see that? And so essentially it's saying the minimum of these two, right? So in this range, because you clip it. You don't want it, I guess, to become too extreme, and you kind of want it to be within its space. And this is for the total value of ratio and the advantage function. Okay, the ratio, I'll write it down, although we expressed it in log space, right? Ratio theta is really, you'll see it written in the paper as something like policy, which is the GPT, theta, because this is the thing that is being updated or trained. I think it's going to have, like, the normal formulation is A and T, like action and state. So we could skip that part if we like. And then theta, old, or old log probs versus new log probs. Do you guys see that? So this is, it goes in the denominator. So actually, let's get rid of that part. And let's just keep it simpler. We're going to say theta old. Do you guys see that? So this is the ratio, which is this, between the old, the new and the old. And this would not be log probs yet. If it was log probs, then we would subtract, okay? The advantage function, this A star, you'll see in there, so, or A hat, is called the advantage function. It helps to determine the relative value of the current action via the feedback from the reward model. So it is related to the reward model. Okay, and it might be that they scale it or they do some kind of thing, but it is coming from the reward model. That's why in my simplified version, I only have the reward itself. You see that instead of some additional function. But you guys can take a look at that. So yeah, that's essentially the formulation that you might see in the paper. But as you can see, it's the same thing, right? So, the ratio is what we're optimizing. It's multiplied times some function that is derived from the reward called the advantage function. And I skipped this part completely, but this is just some clipping, which apparently is really important to control. And you can read that in the paper as well. Okay. So if we were just calculating the reward, then our goal would be to maximize. But in this case, the goal of the ratio, I'm trying to think, that's one thing I'll probably have to read the paper again. All right, yep, so that should be it as far as the notation and everything. Anything else? Any questions? All right, so I think this is a good stopping point. Okay, so that finishes this lecture on PPO. And, talking about this is relevant because this is how you guys have a homework assignment where you're using TRL and you're trying to update the GPT given a BERT reward model. So it's the same mechanism, and now we've discussed kind of the underlying theory of how PPO would update that GPT in a very simple case. All right? For more comprehensive, read the paper. All right, so yeah. All right, so we can stop here for today. I was going to talk about the DeepSeek one, but I think, we can save that for some other time. All right, so I'll stay for a few minutes if you guys have any questions. Otherwise, please don't forget that we have exam 1 a week from today.